3.3 problems. Number 1, we're going to donate an acid to these solutions here. Now, an acid is a proton giver, an H plus giver. So what would be the acceptor in these salts? Well, not the cation, not the silver, the calcium, the cadmium, that kind of thing. It's going to be the anion that's the proton acceptor. And remember, H plus is a proton. Hit pause and give that a think if you need to, because they might say that, a proton, and they mean H plus. So if you donated a proton to this anion, what would you get? Now in this case, what you'd get is a strong acid, and they do think you know your strong acid and base list, and HCl is probably the classic strong acid. So if you try to form HCl in an aqueous solution, you get nowhere because HCl comes apart. That's why it's a strong acid. So the donation of H plus to Ag plus and Cl minus separated in water won't do anything because the H plus won't actually attach the Cl. So the amount of Cl minus running around free in the water will remain unchanged, and the solubility of the AgCl will remain unchanged because you didn't affect the concentration of either one of these. It would never have attached to Ag plus in the first place, and it has no real ability to attach to Cl minus. The same goes for here. H plus would never attach to Ca plus 2, and trying to attach it to SO4 is going to happen very, very little. Now, you may have heard that the Kas for SO4 are different. In other words, the first H plus might attach a bit, and the second one attaches basically not at all in the presence of water. But even that first H plus attaches to SO4 very little. In fact, we might, for these purposes, call it close enough to 0 that it doesn't really affect anything worth talking about. So you're trying to form a strong acid by attaching H pluses to SO4, but you can't because it's a strong acid. It would come apart in water again. So that's also what's happening when you try to attach H pluses to Br minus and Cl minus again, same reason. You can't do it because those are strong acids and you can't form attached strong acids in water. That's why they are strong acids. They come apart in water. Whereas in this case, if you take the anion and try to attach H pluses to it, you get something that is not a strong acid. It's a weak acid. So does some of this actually form? Yeah, some of it does. It actually forms. And that removes some of the S minus 2 from the aqueous solution. And that means that on the right side of your equation, you've affected the concentration of the S2 minus, and you've therefore affected the solubility of the CDS. If we draw CDS and the dissociation equation, we get that. So if you removed some of this because you tied it up in here, by Le Chatelier's principle, we removed something on the right, which makes the left side the more powerful side, and this whole thing will slide to the right. And so we discussed this in the previous section. When you remove some of the ion, you make the solubility go up. If you dose it with S2 minus, you made the right side the more powerful side, and by Le Chatelier's principle, the equation will slide to the left, and it will make it dissolve less. It will make it deposit the solid more, and the molar solubility will go down. Now that's if you add this S2 minus. What we've been doing is removing it by attaching it to H2, two H's. We've been attaching it here, and so the molarity of this has gone down. Also, if you add H's to this, you make something that, or even this, that is not a strong acid. I know it kind of seems like it should be, but that's not a strong acid. This is very much not a strong acid. And H2CO3 or HCO3 minus is not strong acids. And as a matter of fact, here's something practical. CO3 plus acids tend to make water and carbon dioxide, which goes back to another principle I think I've mentioned before. These are low energy molecules and nature loves to make them. And I would write it down. If nature can make water, it probably will. If nature can make CO2, it probably will. And you've given it an opportunity with only minor rearrangements to make both of these when you feed it H plus. Just feed it two H pluses and you can rearrange to this. And that's what happens, by the way, when you remove hard water stains with acids. And you know, for a practical point here, if you get that hard water stain in the toilet, one of the things you can do to get rid of it cheaply, if you do it soon enough, is leave vinegar in it overnight. And vinegar, as we will learn, is acetic acid. It's an acid that won't burn you. I mean, it doesn't taste very good straight, admittedly, but it's not going to chemically burn you. But if you leave it in it overnight, the H pluses from the acetic acid will attack the carbonate compounds in the hard water. And in fact, this is one of the compounds of hard water. The other tends to be magnesium carbonate. And what you tend to get is this forming from the carbonate ions here. And you get water and carbon dioxide, and that loosens it, and then you can scrub it out a lot easier. So the principle here is if you add a strong acid to these, if you remove some of the anion, the solubility will go up. However, if adding a H plus tries to create a strong acid, like with this one or that one or that one or that one, the effect is nothing. On 2, it might help to write out the dissociation reaction. Eventually you'll get to where you can do these in your head, but maybe it's better at the moment if we write it out. And what are we looking for? The magnesium ion molarity. Okay, so we can see that magnesium ion molarity is going to be S. So what we're going to do is take this to the first power and this to the second power, and for the nth time we get 4s cubed. So we're going to divide by 4 using the k value provided here. And then cube root that answer and we get S, and magnesium ion concentration is S. Now be careful, because if, for instance, if they'd asked for the F minus molarity, we'd have to say that the molarity is 2S, is twice this value. In this case, though, magnesium ion is the S value. So what would happen if you dosed it with sodium fluoride? So you've dosed it with fluoride before we even get started, and this all comes apart, and then you only get 1 F for each formula unit of this. So the fluoride ion molarity is that previous to even getting started. So what you end up with is not just 2S, but also plus the amount that you dosed it with. So we put that in. And in this case, remember, the F molarity is squared like it was up here, right? Now this sets up a quadratic formula, but we're going to do this. If the KSP is that small, we can assume that the amount being added by the dissociation of the solid is so small compared to 0.3 that we're just going to cross it out. It won't mathematically matter. You can run it through if you want. You can find the value of S and put it back in and see, but it won't matter once you round off. And then we've got something that we can solve algebraically pretty easy. And we get S is this, and we were looking for magnesium again. Well, magnesium is S. Now, if we pre-dosed it with F minus, it should run back this way, and the solubility of this, this should go down. And as we dosed it with this should get used up. So does this go down when we dose it with F? And yes, it does, by quite a lot. Here's our molarity of magnesium when we pre-dosed it with fluoride, and here it is normally. So it went down quite a bit. On 3, we want to find the molar solubility of cobalt-2 sulfide, and that molar solubility is S value, and they pre-dosed it with cobalt-2 chloride, which sounds similar enough that for a moment when I read it, I got confused and said, oh, they pre-dosed it with the same thing, but it's not. And if this is the solid that we're discussing, then the point here is that we've dosed it with cobalt-2. So we've preloaded it with cobalt-2, pre-dosed it with this ion, so the value of the cobalt ion is not going to be just S, because normally we would get one of these and one of those when this stuff dissolves, but we've pre-dosed it with this molarity. So we get this that we started with plus whatever dissolved, which is S, and then this is also S. Now, this would set up a quadratic formula situation, except this KSP is extremely small. And so it's very, very easy. In fact, we could do this. You know, it's very, very much smaller than that. The S is going to be much, 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 much smaller than that. So it's very easy to say that the amount contributed by the solid is so small that we'll just ignore it. And then we have something that's very solvable. We solve for S, and that's the molarity of the salt that can dissolve. It's the molar solubility. In 4, we're given a KSP for silver phosphate and asked what the solubility would be in pure water, and then if we predose it with this, which we'll get to in a moment. So the molar solubility is the value of S. So here's our reaction, and you probably learned to do this in your head, but it might help to look at it written out this time. And so we got 3 of these and 1 of those. So we're going to have if this is S, this is 3S because we get 3 times as many of them, but then it is also taken to the power of the number in front. So while this is to the power of 1, this is the power of 3, and we get this. So we end up with 27S to the 4th. So to get S, we divide by 27, and then we take the 4th root. And I will remind you that the 4th root of something is also that something to the 1/4 power. So when you divide by 27, take that answer to the 0.25 power to arrive at S, and that's the molar solubility. Don't forget the unit. On B, we go back to the fact that we've pre-dosed it with silver nitrate, and we know that nitrate is a super soluble ion, so this all splits when it hits the water, and we only get 1 silver for every formula unit of this, so the molarity of the silver ion is the same number. So we started off with 0.02 molarity silver ion before we even get started dissolving stuff. So whereas we said this will create 3 silvers and we will get 3S, excuse me, we'll get 3S, right? We started with 0.02, so we get 0.02 plus 3S, and that quantity would be cubed. However, that sets up our extreme nightmare. It's even worse than the quadratic formula, and besides, it doesn't matter what formula it would be because this KSP is so small that let's just do this because it won't matter. The amount that gets dissolved is so low compared to even 0.02 that we can just cross it out and get the right answer once we round off anyway. That's what this means. Let's assume it's really small. And when I cross it out, I get something that I can actually manage. And here's the value of S if it's dosed. And just to confirm, if we predose it with this ion, anything on the right, it should shove the equation back to the left, and the molarity, the molar solubility should go down, and it did by quite a lot. This is able to dissolve a lot less if you predose it with one of the component ions on the right side. On 5, we start off with equal molarities of these 2 anions, and then we're given a KSP for them combined with lead, which is a big clue. And we're told that we're going to slowly dribble in lead nitrate, and we know that nitrate is a super soluble, so all that's going to come off, and we're going to be effectively dribbling in lead for all practical purposes because we're going to ignore the nitrate. So we might form this and we might form that, but which one will form first? Well, the one that needs the less lead to precipitate will form first. Which solid will form first? The one that's easiest to form, the one that needs less lead. So when will they precipitate? When they reach the proportions of the ions that make a saturated solution that sets up an equilibrium. So we're looking for a saturated solution, an equilibrium point, equilibrium solution, and that's where K is true. So we're looking for the point where K is true, given that we're starting with these values for the anions. So if K is true at the precipitation point, and these values are also true because that's the way we set them up, we can solve for the lead value that would make K be true, given that these are true. So here's our values for the lead molarity that will make K be true. Also, we needed to maybe write these out and set these up so we know which ones to square. We're going to end up squaring the I, don't forget that, and we're going to square neither of these. So maybe hit pause and work through those and see if you're getting these answers. But this is the one that needs the less lead by quite a lot to precipitate. So this one will precipitate first. On B, it may be a little hard to even understand what they're talking about, and I think that was not that elegantly phrased, but maybe if we cheat for a moment and look at what we're solving for, it might help. We're solving for the carbonate ion. So to explain this more thoroughly, what they're asking for is, you know how this one precipitated first? When this one starts precipitating, what would the carbonate ion be when that happens? Well, what will be true when this one starts precipitating? Now, I can't apply this K value to this reaction, but what I can say is that when this one starts to precipitate, the lead value will be this amount. It will be this molarity. So when this one starts to precipitate, the lead value has to have reached this point. So what would this value be when that's true? So I'm going to borrow this number and put it in for the lead value. The K has to be true for this because, in fact, we keep pushing the ions in for this. We keep giving it more and more lead, so the K keeps being true. We didn't make less ions available, so that we keep trying to exceed K, except that won't happen, because if you try to exceed K, you just make more precipitate, but you keep a saturated solution. You keep an equilibrium state going. So the K will continue to be true as we add more and more lead, but the carbonate ion concentration will go down. So when this starts to precipitate, this lead value will be true, so I'll borrow that and put it here. And what will the carbonate value be? And that's what's represented down here. So I borrowed the lead value. K has to be true for this reaction. And what would the carbonate ion value be? Well, now we can just divide and get the carbonate ion value when the lead reaches such a molarity that this one starts to precipitate too. I'd like to make a further point about what I meant that K keeps being true even though we keep putting in lead ion. So we had a certain amount of carbonate ion, and then we dribbled in lead ion, and at some point they reached a proportionate level above 0 molarity where K became true. And this is not the scale, but let's say we had this much CO3 ion and then this much lead ion, and at that point the product of these became equal to K. That is where the maximum amount of ion has been reached. That's a saturated solution, and you start setting up an equilibrium. That's where you can't put in any more of either one of these without making a solid. So when we hit that amount of lead, any tiny, tiny fraction, a billionth of a molarity more, and you start making solid. So as we kept dribbling in lead and it kept going up, all we really did was make more solid, and then this kept getting used up and going down. So as this went up, this went down, and solid got made, but K remained true because we are still at the maximum amount of proportion of these that we could have in solution. So we still have a saturated solution, even though this is going up and this is going down. We still have the maximum amount in the aqueous solution, and K is still true. That's what I meant about K is still true, and then we can use it in part B over here. For the old 2001 question, we start off real easy, and all we're supposed to do is write out the dissociation reaction, and we'll get one of these and one of those. So this is our dissociation reaction. Calculate the solubility of the salt in water, but they told us we can get this many grams in this much liters. And so you can parse your way through this. I think of it like this. What do I need for molarity? I need moles and liters. So I'm going to take my grams, convert it to moles with my molar mass, and then divide by the liters I have. And don't forget to call that 0.1 liters here, and then we get molarity. Here I'm asked to calculate KSP, and I know I get one of these and one of those, so the amounts of these in molarity are going to be equal. Now I must be able to know this molarity, or I can't find that, and I do because when I dissolve, say, 5 of these, I get 5 of that and 5 of that, and I do know the molarity that I can set up from this. I just figured that out here. So whatever molarity I can dissolve of this is also the molarity of this and that. So I'm going to grab this number and put it in for each of these, and that's why that ends up squared, because it's multiplied by itself twice, and then I get KSP here. on B, it gets a little confusing because we get two KSPs, but look what we're working with, sodium chloride and lead 2 nitrate. And I know that nitrate and sodium never figure into any K math because they're super solubles and they would never form a solid. So let's just disregard them. And we're effectively working with Cl minus and Pb plus 2. So this is the KSP that I want to work with for part I. So what's the question? Will there be a precipitate? Well, there will be a precipitate when the current molarities present in the beaker are high enough that you reach or exceed the value of K. And so when you remember, when you do K math on the current values and you're not sure if it's at equilibrium, we call that Q. So we're going to take the Q value and see if it meets or exceeds K. To get Q, I need molarities, current molarities of the ions. So we took this molarity of that and this molarity of that, and notice they made it a little easy because they have equal volumes of each. So if you add equal volumes, then the volume doubled, and you could just kind of skip this and logically say, if the volumes for both doubled, then the new molarity for both of them is half of what it used to be. Now we have molarities we can use. And the other thing that's really easy to forget is that when we set up the dissociation reaction for this, we're going to get 2 chloride ions. So the value of the chloride ion is squared. This is the first power, and that is squared. So don't forget to square that, and we get Q equals. Now, does Q meet or exceed K? No, it doesn't. It's definitely smaller than K. The molarities are not high enough to reach K. This is not a saturated solution, and there will be no precipitate. In double I, it's phrased a little bit oddly, but it might be easier to think of it this way because we're going to get the same answer. We have pre-dosed our solution with this much of NaCl. Now, in actuality, I think it comes after, but in effect, it's the same thing. And we have a saturated solution in which we know that there is an outside influence of this much, 0.25 moles of the chloride ion, because of course all the sodium came off. It's a 1 liter solution, so this many moles is the same amount molarity. So you can think of it as starting with no lead and starting with 0.250 molarity of Cl minus ion. So this dissolves, but this already outweighs the amount given by quite a lot. So let's just scratch that out. The amount of chloride ion contributed by the actual dissolving of the solid, it doesn't really count for anything. So let's just scratch it out. Don't forget to square it here. And so we get this amount, and the amount dissolved, well, we'll scratch it out, and we'll just leave it as the amount contributed from the outside NaCl. Then we have something we can solve pretty easily, and we get a value of S, and that is the molar solubility, but we were asked for the lead molarity, and just double check, what is the lead molarity? Well, that was the one that was S. So when we find S, yes, we have found the lead concentration, lead molarity, but actually state the answer. Do not just leave it here. That is not answering the question. You didn't state that the lead ion is this molarity. So actually write this out. Don't forget that, because I'm sure that the test graders will charge off for that. And if it's a short problem, you may get 0 out of 1 for not actually answering the question. In triple I, we're adding in NaCl to a beaker. And I know that Na won't count in any kind of K or KSP math, so I'm just going to cross that out. It's a super soluble, it won't matter. And I'm adding it to silver nitrate. Nitrate won't matter, I'm going to cross that out. And lead 2 nitrate, nitrate won't matter, I'm going to cross that out. So basically this molarity applies to the silver ion, and this molarity applies to the lead 2 ion. So which will precipitate first? So we're going to have to go back to the part at the beginning of B and grab the other KSP. But here's my dissociation reaction for the silver chloride, and here's my KSP setup then, and the silver ion is already set up as this amount. So what chloride ion would it take to get this to precipitate? In other words, what molarity of this would it take for K to be true and start the precipitation? So I'm going to solve this, and they wrote it out, and it's solved for Cl minus already, and this is the molarity of Cl minus it would take. This is a bit odd that they wrote it out like this. I'm not saying they're wrong, but here's our dissociation reaction. Remember that Cl minus is going to be squared then. We pre-dosed this with lead ion back here, this molarity, so that goes here. And we're asking what chloride ion concentration would it take for K to be true, because that's the point when the precipitation will start, when K is true. So if K is true and Pb plus 2 is true at this molarity, what would the Cl minus molarity have to be to make K be true? And so we're going to solve for x squared, or you can look through this version, and we get 0.01. So which one's smaller? Well, this one is smaller by a lot, a lot. And so it's going to take less Cl molarity, Cl minus molarity, to make this precipitate. This will precipitate first by quite a ways.